Okay, good morning, everyone. And today we will continue with the topic about the matrices for radioactive waste. And today we will look on the possible radiation effects on the matrices and what is the nature of these effects. So it will be some equations, some formulas. I hope it will be not so scary for you. Let's start. And again, this picture about the uh, importance of the multi-barrier system. And one of these barriers, of course, itself is a matrix of radioactive waste. And when we are looking on what is happening with matrix or any other materials when it interacts with ionizing radiation, first of all, we should remember that all our space is filled with electrons, not so the atoms, the size of atom is 10,000 times more than size of the nucleus. So all the space is filled with electrons. That's why all the interaction of ionizing radiation, either it is alpha, beta particles, gamma radiation, whatever, all of these types of radiation, they interact firstly with electrons. And as far as it is mainly interaction with electrons, we can see the effects like ionization or excitation of atoms, but also as far as the energy of this ionizing radiation is much higher than energy of any of chemical bonds. That means that due to this interaction, chemical bonds can be destroyed, can be damaged, and we can observe also the displacement of the atoms. What is also important that when we are looking on the energy of alpha particles, for example, usually the range of energy of alpha particles from radioactive decay, it is from 4 to maybe 6, 8 mega electron volts. Is it big number or not? For chemical reactions, it is huge value, because normally the energy of chemical bonds is just few electron volts. And the energy of alpha particles or beta particles, it's a kilo or mega electron volts. So it's thousands or even millions times larger value than energy of any of chemical bond. But also, when we are speaking about the energy of alpha particles, very often people forgot about the so-called recoil nucleus. But the energy of recoil nucleus is also very high. It's something like 100, 200 kilo electron volts, depending on the energy of the alpha particles. So this energy still 10,000 times higher than energy of any of chemical bonds. That means that when we are looking on the effects of the ionizing radiation, when our ionizing radiation is inside the material, it is not only interaction with this alpha or beta particles, but also a huge impact of the recoil nuclei. And again, as far as the interactions, they are mainly with electrons. That means that we can observe also this type of interactions. So it's inelastic interaction. That means that part of the energy transferred to our material. And we can observe either excitation when our electrons, they are going to the higher energetic state and then they go back in the ground state. Or we can observe ionization. That means that the energy is high enough to take our electrons out of the atoms, and thus we form positively charged ions. And maybe if it is homogenic destroy of the bonding, we will observe the formation of radicals. If we will look inside our radioactive waste, what are the elements mainly, or radionuclides are mainly present there? It is either actinides. They're not very much amount of actinides in nuclear waste, but still they can be present there. And actinides or any other heavy radionuclides, they predominantly have alpha decay, yeah? So the formation of alpha particles. All the other fission product and activation product, they have mainly beta minus decay, so the formation of beta minus particles or electrons. Yeah, so they have excess of neutrons. That's why the neutrons decay to the protons and release electrons, or what we call beta minus particles. Also, due to the decay, usually the resulting nucleus is not in a ground state, but in excited state. So that means that there is also the transformation of the excited state of the nucleus to the ground state and the emission of gamma rays due to this process. So again, mainly we observe beta minus decay, gamma radiation, and sometimes alpha particles formation. The beta minus radiation mainly comes from the fission products, but also from the active product of the activation of different materials. Yeah? Activation means that neutron is captured by nucleus and another nuclide is formed. And then there can be further decay of this cobalt-60, it's beta minus, etc. It can be activation of the structural materials like steel or some concrete or zircaloy, and the formation of all these radionuclides. Some of them are really difficult to determine, for example, like carbon-14. Yeah, it is pure beta emitter. There is no gamma radiation from carbon-14, so it's really difficult to determine the amount of this carbon-14 in the material. You need to make some chemical operations, and we will talk about it on our next lecture about the destructive characterization of radioactive waste. But so you have to perform some additional operations to be able to measure such radionuclides. So now we will go in not very deeply, but we will look on the interaction of different types of ionizing radiation with matter, just to understand how we can, not only how they interact, what are the consequences of the interaction with the matter, but also this information will be useful for us for our next lecture on Monday about the non-destructive characterization of radioactive waste, where we will speak mainly about gamma spectrometry and some neutron activation spectrometry. So we need this information because it is a basis for the detection also of the ionizing radiation. So we will start with the heavy charged particles, and heavy charged heavy particles means the protons and all the particles heavier than protons. Why they are heavy? Because it is comparison with the mass of the electron. Electrons are very light particles, and one proton is around 2,000 times heavier than electron. Yeah, so it's heavy particles compared to the electrons. And alpha particles, they consist of 2 protons and 2 neutrons. So 4 masses of protons, let's say, and in total, it's around more than 7,000 times heavier than electron. So these huge, not huge, but heavy particles, when it goes through the cloud of the electrons, very light particles, these alpha particles, they don't feel electrons at all. That's why their trajectory, their trace is a linear. Yeah, so it's just a straight line because electrons are too light for the alpha particles. And they don't feel electrons, these alpha particles. And only when alpha particles interacts with the nuclei, they have this change of the trajectory, and there is this change in trajectory. So mainly it's a line, and the alpha particles, they ionize all the molecules that they meet in their pathway. But also, alpha particles, they are so energetic that when they ionize the material, the electrons that are released due to this ionization, they have also quite a big energy. So it's something like 100 to 100 electron volts. Of course, it's much, much less than the energy of the alpha particles, that is 5, 6 mega electron volts. But still, this energy is high enough to ionize other atoms. So it is the secondary ionization by so-called delta electrons. And this secondary ionization or indirect ionization produces around 70 to 80% of all ions in the metal. So we have this very concentrated trace of ionized molecules, but also due to this secondary ionization, we produce much more ionized particles inside the matter. It's interesting that the higher the energy of the alpha particles, the lesser the ability of alpha particle to ionize the matter. It can be simply understood because the higher the velocity of alpha particles or the energy of alpha particles, the less the time, the contact time of alpha particles with some certain atom. That means that it is not enough time to ionize this atom or molecule for alpha particle. So the higher the velocity of alpha particles, the less ionization it can produce per 1 micrometer of its pathway. But as far as the energy of alpha particle decreases, or that means the velocity of the alpha particle decreases, the larger the contact time of alpha particle with molecules or atoms, and that means the higher probability of ionization of the matter. So that's why with the decreasing or decelerating, with decreasing of energy of alpha particles, or that means decelerating these alpha particles, we increase the probability of the ionization of the matter with alpha particles. But at some point, when the energy is already low enough, or that means the contact time is large enough, alpha particles, it is has charge +2. Yeah? So that means that if these highly charged particles moves very slowly, it can catch 1 electron and becomes not +2 but +1 charged particle, and the ionization probability decreases. So after catching 1 electron, the energy, the production of the ions decreases because the ability of the +1 particle becomes lower. And with the decreasing of energy, the second electron can be captured, and it is not more alpha particles, it's just an atom of the helium, neutral atom of helium-4. So there is no further ionization. This curve results in the so-called Bragg curve that shows us the ionization by the alpha particles depending on the range of the penetration of alpha particles in the matter. In the very beginning, when alpha particles just comes in the matter, the energy of alpha particles is very high. That means that ionization is low. But due to the energy losses, when alpha particles goes through the matter, it step by step loses its energy. The ionization is increasing, and at some point when alpha particles catches electrons, no further ionization occurs. So there is a maximum of energy losses at the very end of the pathway of the alpha particles. So there is almost, so not absence of the ionization, but the ionization is not so high at the very beginning, and all the maximum of the ionization is at the end of the range of the alpha particle. So if we will look on the flux of the alpha particles, we will see that it is 100% of alpha particles that goes through the matter, but at some certain point, immediately all the alpha particles stopped. So there is only a very small fluctuation of this range of the maximum range of the alpha particles penetration. So interaction of beta radiation. Beta radiation is simply electrons, but what is the difference with the monoenergetic electrons? That beta particles, they have a full range of energies from the 0 to the maximum energy of the decay. There are specific interactions of the electrons. Again, just a reminder that electrons, they are light and one-time negatively charged particles. As far as they are light, they interact with other electrons that results in a broken pathway. So it's a lot of scattering of these electrons. And there are two specific processes that is called Bremsstrahlung or stopping radiation and Cherenkov radiation. So again, due to the very low mass of the electron, the average angle of the multi-scattering of the electrons is very high. Also, if we increase the mass of our material or the charge of the nuclei in our material, we also increase this average angle of multi-scattering. So that means that for very heavy elements like lead, for example, or iron or copper or whatever, we can observe even backscattering of the electrons. This angle will be very high. So what is the so-called Bremsstrahlung? Again, it's breaking or stopping radiation. From the physics of charged particles, we know that if the charged particles moves with acceleration, it creates electromagnetic waves. But acceleration doesn't mean that we only increase the velocity. Acceleration can be with sign minus, so it can be deceleration. And it also will produce the electromagnetic waves. Also, when we change the trajectory of the charged particle, it is also the movement with the acceleration. And due to the change of the trajectory, there is also a formation of electromagnetic wave. So all this either stopping or changing the trajectory will produce so-called Bremsstrahlung. And this effect, the formation of the electromagnetic radiation due to the change of trajectory, is used in synchrotron-based methods for analysis of the materials. And I hope the next week Peter Matveev will make a presentation about these synchrotron-based methods for characterization of materials. So anyway, you can see that the intensity of this electromagnetic radiation is dependent on this acceleration squared, and acceleration itself, it is reverse ratio of the mass. That means the lighter our particles, that is changing the trajectory or stopping, the higher the intensity of the radiation. So as far as the beta particles or electrons, they have very low masses. That means the intensity of this stopping radiation is very high. If we compare the intensity of this stopping radiation produced by electrons and by alpha particles, we will see that the difference will be something like 50 million times less intensive radiation from alpha particles. So alpha particles or heavy charge particles, they also produce this Bremsstrahlung, but the intensity of this radiation is so low that we neglect it. Okay, so we mainly talk about this breaking radiation for electrons. And you can see that, so normally this, or practically, this stopping radiation is used in X-ray sources for example, X-ray diffraction analysis or any X-ray based techniques, X-ray fluorescence analysis, X-ray photoelectron spectroscopy, whatever. They use these X-ray tubes, and these X-rays, they are produced due to this stopping radiation. So you have cathode and anode, and the flux of electrons that are going from the cathode, and they this accelerated electrons, they are just stopping at the anode, and they produce this X-ray radiation. So this is very useful radiation for many analytical purposes, but for us, it is dangerous phenomenon. Why? Because if we will look, for example, on lead, if we know that we have a source of beta radiation, and we put some lead shielding for these beta particles, that means that that we will produce quite a lot of Bremsstrahlung, or this breaking radiation. So it's X-ray radiation that goes from the shielding. So, and if we will not calculate properly our thickness of the shielding, that means that we will generate X-ray radiation, and this X-ray radiation will irradiate the operator. So this phenomenon is sometimes is very useful for analytical purposes, but also is very dangerous if you will not take this phenomenon into account. Another effect, it is so-called Vavilov-Cherenkov radiation. It is a very interesting phenomenon. We know that there is no particles that can move faster than light, but with one requirement. They cannot move faster than light in vacuum. But it is not true for other media. For example, the speed of light in water or in other medias is slower than in vacuum, and it can be calculated if we divide the speed of light in vacuum by the refractive index. So for water, this refractive index of 1.33. That means that it is only 75% of speed of light in vacuum that we observe in water. And for this speed of light, the energy of electrons is equal to, let's say, 270 kiloelectron volts. And if electrons are moving faster, or they have higher energy than this value, that means that they move faster than light in this media. And you can see that there are quite a lot of, just a brief list of the common radionuclides with the maximum of energy of the beta particles much higher than this value. So what's happening when the particle moves faster than the speed of light in this media? It creates this radiation, the radiation of light. It is can be maybe not the very correct comparison with the air. When some object moves faster than the speed of sound in the air, it creates this also, let's say, radiation or boom. And that means that this radiation, let's say, it produces not by the object, but by media where this object is moving. So the same is here. When the electron moves faster than the speed of light in the media, it makes the media itself radiate the light. So it moves faster than light, and it produces light in media. So the media itself irradiates lights, not the particle, but media. And the spectrum of this light, of this Cherenkov radiation, is blue-violet, in blue-violet region. That's why we can see on different pictures of nuclear reactors this blue irradiation. So it is Cherenkov radiation that produces by highly energetic beta particles in the water. So that's why these pictures of in pop culture of green light of radiation is not true. Better to use blue color to show the radiation, because actually in air we have some moisture, and really, if we take very active powder of cesium-137, for example, we can see the blue light of this powder due to the Cherenkov radiation of that produces in moisture in air. So actually, it's not green; it should be blue. Okay. Attenuation of the beta particles flux is not linear. In the very beginning of its range, we can use exponential law of this attenuation, but due to the fact that the distribution of the energy of beta particles is not homogeneous, let's say, there is no simple mathematical law to calculate this attenuation. So normally we use empirical dependencies of the attenuation of fluxes of the beta particles depending on the thickness of the target where the beta radiation goes. But for monoenergetic electrons, this attenuation is rather simple. It's almost linear attenuation of the flux. The thicker the target, the less the flux of the monoenergetic electrons. And sometimes we have positron emitting radionuclides in our system, and positrons, they're very similar to electrons. When positrons just emitted, they have also very high energy, and they behave absolutely the same as electrons. But when positrons stop, the positrons, it is electrons with the positive charge, so anti-electrons. When the positrons stopped, so they can interact efficiently with the electrons, then they annihilate with the electron. There is no more physical particles, but due to annihilation, two gamma quanta are produced, or annihilation photons, let's say, both with the energy of 511 kiloelectron volts. So 511 kiloelectron volts, it is a mass of the electron in the rest. If we use this equation, energy is equal to mass C squared. So we can recalculate it, and it will be 511 kiloelectron volts. So it is mass of one electron. But as far as there are two masses of electrons, positron and electron, that means that we produce two quanta with the same energies, and they goes in opposite directions, because when again this annihilation occurs when the positrons almost completely stopped. That means that momentum is zero for the positron, and there is a law of conservation of the momentum. So this formed particles, they must go in opposite direction to have total momentum equal to zero. And this used in positron emission tomography, probably you've heard about it. So now interaction of gamma radiation with matter, and gamma radiation, again, it is a result of almost all the decays in radioactive waste. Even for cesium, cesium-137, we know that after the beta decay, there's formation of barium 137M, metastable barium, that goes to the ground state with the emission of the gamma radiation, with the energy 662 approximately kiloelectron volts. And gamma radiation, it is pure electromagnetic radiation, so there is no mass. That means it is very high penetration ability of this radiation. And we will look on three main interaction mechanisms. It is photoelectric effect, Compton scattering, and electron-positron pair production. So what is the photoelectric effect? It is very, again, useful for us effect, because in this case, the whole energy of gamma quanta is absorbed by the electrons. But this energy absorbed by the electrons is so high that electrons goes out from the atom, so it knocks out from the atom. That's why there is a formation of the vacancy on the nearest electronic shell nearest to the nucleus, and there are two main consequences. It is either formation of the characteristic X-ray radiation. Why it is happening? Because this vacancy is filled with the electrons that goes from the upper electronic shells to the lower electronic shell, and there is a differences in the energy of these two electronic shells. That means that there is excess of energy when electrons goes from the upper to the lower electronic shell, and this excess of the energy is released either in the form of the characteristic X-ray radiation, or this energy is transferred to the upper electrons, and again this energy is enough to knock out these upper electrons, and they goes out from the atom again. And so there's additional electrons that are going from the atom as a secondary process, and it is called Auger electron. So it's the surname of the French physicist Auger. So again, it is good processes, because all the energy of gamma quanta is absorbed in the matter, so we can shield ourselves from the gamma quanta if all the gamma quanta interacts with the photoelectric effect. So you can see that the heavier the element, so the higher the number of element in the periodic table, the more efficient, the more probable this photoelectric effect. That's why we use the very heavy elements like lead, for example, to stop the gamma quanta, because again, the higher the atomic number, the higher the probability of this photoelectric effect. That means the total absorption of the gamma quanta energy. Unfortunately, it is not the only effect. Another effect is Compton scattering. When part of the energy of the gamma quanta is absorbed by the electrons, and as far as only part, another part scattered, let's say, scattered as another gamma quanta with lower energy, but still it is the scattering of electromagnetic wave with lower energy, but still with high enough energy to irradiate everything. So here again we produce some electrons, because this energy is still very high, and it's enough to knock out this electron. And electron positron pair production, for me it's like a magic, because in this case, in the beginning we have only electromagnetic wave, so no masses, just pure energy, let's say. And due to something due to interaction with the field of the nucleus, this electromagnetic wave, this pure energy, converted to some material particles, to the positron and electron. So it's really like a magic. But to do this, the energy of the gamma quanta should be more than 2 masses of the electrons, because you see it produces electron and positron, 2 masses. That means that it's possible only if the energy of gamma quanta is more than 1022 kiloelectron volts. And the higher the energy of the gamma quanta, the more probable this effect. So if we will look on the probability of these three effects, we can see that at some certain value of gamma quanta, the higher the atomic number of the atom, the more probable the photoelectric effect is becoming. Or if we have some certain material, we can see that the higher the energy of gamma quanta, the more probable Compton scattering first, and then pair production, positron-electron pair production. These lines, it's not just a strict border between two effects. It's just a relative probability of the effects. Here, this line means that at this point, it's 50-50 photoelectric and Compton scattering. If we go to this area, it doesn't mean that it's pure photoelectric effect. It's just more probable photoelectric effect, but it's still some part of Compton scattering. Okay, so don't take this picture as like absolute values. It's just some relative, more probable effects than others. And attenuation of the gamma ray radiation is quite simple from mathematical point of view, just the exponential decrease with the increasing of the thickness of the material. And so again, the attenuation depends on the thickness of the material and on the composition of the material. The higher the atomic number of the of the material, the higher the attenuation of the gamma radiation. So very simple. So if we compare the penetration probability of different radiation, we know that alpha and beta radiation can be easily absorbed by any material, and gamma radiation has very high penetration ability. But if we are talking about the storage of the radioactive waste, when all these packages they standing very close to each other, and if radiation even goes from one package, it goes to another package. So in this storage conditions, actually, we can say that all the energy is absorbed in matrix because they standing very close to each other, these packages. So there is no almost no release outside of the energy. All the energy is absorbed in the matrix. And when we try to compare different effects in the matrices, we need to use some units, quantitative units, what is happening. And one of the simplest unit for either for radiation effects or even for radiation safety, yes, it is absorbed dose. So it's quite a simple definition. So it's just the energy that is absorbed in the matter divided by the mass of this matter. So it's joule per kilo, and there is a specific name of this unit, gray. And also, if we want to understand what part of the material destroyed or how many radicals or ions produced in our material, we can use the chemical radiation yield, or very often it is called G value. So in articles, you can see both these definitions, either this or G value. And it's also very simple definitions. It's just a number of some species that are produced or destroyed by the some amount of the energy. If we go to the standard units, in standard units it is mole per joule. But very often in the articles, again, you can see that it is a number of ions or other species per 100 electron volts. Because it's very convenient units, usually it's some few ions per 100 electron volts. So it's not just not these complex numbers. It's just simple numbers like one molecule per 100 electron volts or 1.5. So it's convenient numbers. That's why very often in the articles it is still used ions or molecules per 100 electron volts. But you can easily recalculate one units into another. So if you know definition, it's quite simple. So, and is it a big number, 1 gray, or not? So we can calculate how much, what will be the increase in temperature in water if the dose will be 1 gray. So it's a simple equation from the school of physics. And we can calculate for water that it is only 2.4 10 to minus 4 Kelvin per 1 gray. So it's not very big energy, actually. But again, if we will look in the requirements for the matrices, especially for high-level waste, we will see that the modern requirements says that the borosilicate glasses, for example, should withstand doses up to 10 to 9 gray. So if we multiply these numbers, that will mean that the temperature should be like 100,000 Kelvin. But why it is so big temperature should be in our matrix? And the answer that in this calculation, we assume that the whole energy goes in our material at once, yeah, in one moment. But actually, when we are speaking for high-level waste storages, these dose should be accumulated during the storage of the radioactive waste. It's not in 1 second. It's in something like in 1,000 years. And for this, it is important that our material has a good thermal conductivity, as I mentioned on Tuesday in the previous lecture. And it is one of the example. It is simulating of the cement matrix. If we put radioactive waste with different heat production rate, and you can see that even for very high heat production, so 1 kilowatt per cubic meter, it's really high heat production. Even for these high numbers in cement, that is not really a perfect thermal conductive material. Even for cement, inside the temperature will be not higher than, let's say, 300 Celsius degrees, and outside on the walls, it will be only 90 Celsius degrees. Yeah. So the thermal conductivity resulted in the transfer of heat from the material, and even for such high doses, of course, temperature will be not like 100,000 degrees. Yeah. So it will be maybe 100, 200 Celsius degrees if it is fresh, high-level waste, but not more, due to the good thermal conductivity of the material. So what is going inside from the chemical point of view? We talked about the knocking out of the atoms from their positions in crystalline materials, but also if we have water, yeah, like in cements, we produce different radicals or active species in our material. And of course, they have a very limited period of living time, and they interact with the components of the materials, or they combined and produce some hydrogen or hydrogen peroxide. And again, we can see there are many works on the understanding what is going on in cements. And you can see already obtained these G values. Yeah, so it's a molecule produced per 100 electron volts in the cements. And you can calculate, if you know the dose rate, if you know the time of the irradiation, you can calculate the yield of the different active species in your material. And one of the product is this calcium peroxide. That will be important for us, as I mentioned previously. Also, we can see that the porosity, so it's very scarce data, but still we can see that the porosity of the cement materials is decreasing with the gamma radiation, and the decrease in porosity, that means that material becomes more dense and more durable. The production of hydrogen, as I mentioned on Tuesday, is limited. Also, that means that we can use these materials maybe even for some sort of high-level waste. The release of the gaseous products, or this gas pressure here, also depends not only on total dose, but also on the dose rate. Because if you have a very low dose rate, there is a possibility of the recombination of the different species. So not only the total dose, but also a dose rate will affect on the production of your gases, of your chemical species. Here again, you can see the increase in the mechanical strength of the irradiated cements, and again, the less porosity of these materials. We also performed some study with the ordinary Portland cement without and with high-level waste simulator. So it was not active solution, it just stable elements that were immobilized in this cement matrix, and we irradiate them with electrons and with alpha particles, and you can see that the compressive strength is almost the same with the uncertainties. Also, the mineral phase composition, so there is no indication of the mineral phases, just the comparison of the XRD patterns, but you can see that they're almost the same, just a few deviations. It is interesting that after irradiation, so this before irradiation, it is pink and green symbols, and after irradiation, it is blue and brown symbols. And you can see that after irradiation, the leaching, at least of the nitrates, is lower than for non-irradiated cementitious waste form. So the irradiation results in the more strong materials and more durable materials for cement. So now we will go to the mineral-like matrices. Here just an example of the monocyte matrix, and there is a so-called critical amorphization doses expressed in the displacement per atom, dependent on temperature. The lower the temperature, the better the resistance of the material, because if we can recrystallize the materials at lower temperature, it is good for the materials we don't. What does it mean? If the material that was initially with good crystallinity, and due to radiation, it becomes amorphous. Yeah, so it's a lot of displacements and materials becomes not crystalline but amorphous. But if we heat it, these materials again, that means that all the atoms, they will go to the initial place due to the movement of the atoms. And here, it is the temperature at which this recrystallization occurs. Yeah. And the lower the temperature, the more stable is the material. Okay. So, and you can see that the more with the higher size of the crystallites, the materials becomes more stable. And it is one of the good real examples of this monocyte-like matrices. It was synthesized by our colleagues in St. Petersburg in Radium Institute by Boris Burakov. It is europium phosphate, so it's monocyte, doped with some plutonium, so it's up to 5% mass percent of the plutonium, so it's high enough. And it was stored since 2003, so for nowadays it's more than 20 years. But when we studied it, it was something like 15 years, 13, 15 years. So at that time, it was the irradiation around 5 to 10 to 18 decays, alpha decays per gram. And so it's a really high dose. And you can see that initially monocrystalline phase starts to not decompose, but some blisters or flakes, they started to occur on the surface of this material. And of course, it was interesting to understand what is happening there. And we investigated these materials The bulk materials from the electron diffraction, you can see it is still very good crystallinity with these crystalline patterns. So the material itself in the bulk still crystalline after 12 years. And when we looked inside these blisters or flakes, we observed that they have the same patterns in Raman spectroscopy, for example, as a bulk material. So these flakes, they are mostly the same as the bulk material, as the monoxide itself. We observed some, it's not very good resolution here, but we observed some bubbles due to helium bubbles due to the alpha decay. And the crystalline structure of these materials, so it's not so good crystalline structure, but the patterns of the crystalline structure is the same as the europium monoxide. So from these investigations, we observed that during the storage of the mixed europium plutonium monoxide, these flakes is just pure europium phosphate without plutonium. So it's like a recrystallization of the material in the solid state. So it was interesting. So actually, there is no amorphization of the material, but some recrystallization on the surface of the materials due to the contact with the humid air in lab conditions, just storage in lab conditions. And due to the contact of the humid air, there is a possibility of the recrystallization on the surface of this material. So we can see these defects due to the recrystallization on the surface of the materials. So with time, of course, there will be much more of such recrystallization processes. So, but again, in this case, we stored material just in the air without any coverage, without any, I don't know, putting it in the sealed barrel or whatever. What else is happening with the materials under irradiation? As I mentioned before, it is amorphization of the material. And to compare different materials, to compare the radiation stability or resistance, we compare this critical amorphization dose dependence on temperature. As I mentioned before, the lower the temperature dependence, the better the material, the more resistant the material. Why amorphization is important? Because if you go from the pure crystalline state to the amorphous state, you will increase significantly the leaching rate of the radionuclides. That means that your radionuclides will be easier released from the material if it goes to the amorphous phase, amorphous state. That's why the amorphization is important, because it will result in higher leaching rate of the radionuclides, and it is bad, for example. Another example, it's borosilicate glass. So it's not a mineral like material, but pure glass material. Again, it was synthesized by Boris Burakov in the Radium Institute with some, again, quite high amount of plutonium-238. So plutonium-238 with shorter half-life. That means that the dose can be accumulated much faster. And this, they described that the color is cognac-like color, so this nice brown color. And it was funny to observe the illuminating, self-glowing of the materials in dark conditions. So you can use it, I don't know, in the night for illuminating your room, maybe. Yeah, it was one of the idea to use this material as emergency lights when no electricity is available, but you have this light showing you the emergency pathway. But yeah, of course, it was like a joke, but who knows? But what is interesting here is the condition of this material after leaching. So it was stored in water at 90 Celsius degrees for a few weeks. And you can see the very huge impact on the surface of this material. So it still was under these flakes. It was still a good glass, but the surface was changed a lot. So it's this granular-like structure, the formation of the new mineral phases on the surface, and it really affects a lot on the leaching of the glasses. Also, what is important due to the storage of glasses and due to the radiation and chemical transformation of glasses, it is the formation of these dendrites or microcrystallites of the solid phases inside the glass. And again, due to the radiation, due to the formation of the vacancies in the structure, it makes it easier for elements to diffuse in the glass and to accumulate and form these microcrystallites in glasses. So it's bad situation for glasses because they become not amorphous but crystalline, and it is not good for glasses. When we look on this formation of the vacancies or defects in the material, and there is difference in the formation of the defects by the light ions like electrons, yeah, and by heavy ions, because in this case, when there is a pathway of the light ion, it is low ionization or defect production rate, and it is more like pearls on a string geometry. Yeah? There is a string and some pearls on this string. But when heavy ions go through the material, it forms a displacement cascade, known also as a displacement spike. And when ionizing radiation knock out one atom, what's so-called primary knockout atom, this primary knockout atom can have energy enough to knock out other atoms, so-called secondary knockout atoms. And this cascade form this displacement cascade. And the most usual defect is so-called Frenkel pair, when one atom knock out from its position, so the vacancy is formed, and this atom resulted in the interstitial position, so there is a vacancy and some extra atom not in its position, interstitial position. And these defects, they can migrate due to the thermal movement of the atoms, and they can form either loops or even voids in the material, so we can observe these bubbles inside the materials. And to study the irradiation effects on the materials, we use two approaches. Either the most popular, of course, maybe 90+%, it is external studies, because you can use different techniques with very high fluxes of the particles, and you can create very high doses in a short time. Or you can use internal irradiation, so it is more reliable. It is more close to the real conditions. But for internal irradiation, you have to wait a lot of time, maybe a few months or even years to create the same dose as for external studies. Yeah, these internal studies, when you put your radionuclides inside the matrix and wait for a few months. And for external studies, it is not only electrons or gamma radiation, but also heavy ions that simulate the production of the defects by the recoil nucleus, for example, or by alpha particles. And it is interesting that today there are quite a number of the techniques that can investigate in situ transformation of the material under the irradiation conditions. So there is it's better to see, I think here, yeah, there is a line for the ion flux to the material, and at the same time they can make a transmission electron microscopy of this material, so simultaneously. And in some cases they have not only one ion fluxes, but they have like in UK in this university, I think they have two fluxes, one with the heavy ions like lead or xenon, and one with the another heavy ions, but it is protons and alpha particles. And they can look on the simultaneous effects of these two types of radiation on the material. So it's very powerful technique and very interesting results. And just again, a reminder that today we use quite a lot of these quantum chemical calculations and neural networks to calculate the radiation effects on the solid materials. I showed you this slide on Tuesday, so we'll not go in details for these slides. Yeah. Okay. Thank you for your attention. If you have questions for this part, we have a few minutes to answer. If not, then we can have a short break and then go further with the next lecture. Okay? Thank you. Yeah, it's
And the one for you, how do you know? Guys, I would like an announcement for tomorrow. Look at the channel, okay? I'm up. Okay, great.
Okay, let's continue. And now some information about the destructive characterization of radioactive waste. And on Monday, it will be non-destructive characterization. So let's start with this topic, why we need to characterize radioactive waste. First of all, we would like to know the real content of the radionuclides inside this certain barrel or in patty of packages to understand if our radioactive waste are complementary with our requirements or not. Of course, when we characterize waste, it is always dose rate characterization. So how to, is it safe to handle this waste or not? And there is some certain requirements for components of the radioactive waste, requirements on their chemical properties, because by, for example, Russian regulations, the components of the radioactive waste, they must be not corrosive or explosive, or there should be no biohazard, etc., etc. But today we will talk about the radionuclide composition of the radioactive waste, and just some basic information about the detection of different types of the radionuclides by different techniques, because otherwise we cannot measure them without detection. And again, just a reminder that we cannot see or feel ionizing radiation by our organs, so we can observe or measure ionizing radiation only due to its interaction with matter. Yeah, so there is no other way to determine the concentration of radioactive components. So it's always interaction of ionizing radiation with matter. And so we already know this mechanism. We will not go in detail on in the mechanisms, but as far as we already know the mechanisms of interaction of ionizing radiation with matter, we know the consequences of these mechanisms, and we can use these consequences for the detection of ionizing radiation. Yeah, if it is ionization, it is production of ions, and that means that we can measure the movement of ions. That means the electric current. Yeah, and it is ionization detectors. If it is excitation of our material, that means that there can be light be produced in the materials, and so the consequence is the radiation of the visible light, and thus we can use it also for the detection. Or it is production of the defects, and it is another type of the detectors that are called track detectors. So we can count the number of the events, even that were accumulated for days or even weeks. And we, with the analysis of the tracks, it is not only the measure of the amount of the events, but also the energy of the alpha particles or beta particles, so we can analyze what was the inside and where it was. And we can detect the heat production of the radiation with the colorimetric detectors, but it is mainly for radiation safety purposes. It is not for detection of the radionuclides. So again, if we know the mechanisms of the interaction of ionizing radiation with matter, we can use it for our purposes. And the main characteristics of the detectors So when we measure something, it is not that we measure the absolute activity immediately. Yeah, we measure only some response of the detector, and we have to calibrate this response of the detector towards the real or absolute activity. And one of the main characteristics of the detectors, it is efficiency of the detection. So how good our detector detect this type of ionizing radiation. And the second very important characteristic is the resolution of the detector. And the resolution, it is not only energetic resolution or time resolution, it is also spatial resolution. In principle, resolution is the ability of our detector to distinguish between two events. So, for example, if when our detector detect some decay, yeah, it goes to the excited state, and it takes some time for the detector to go to the ground state, to the initial state. And if this time is very long and another event is happening, this event cannot be detected because our detector is not in the initial state. Yeah, so we will lose the second event. So this time between the two events that can be distinguished is the time resolution of our detector. The same is for energetic resolution or spatial resolution or whatever. And when we choose the certain type of the detector, we should know what we want to detect. Yeah, because it will tell us what the resolution should be. Will we detect very high activity or not? Do we need to have a good energetic resolution? Or we will measure only one radionuclide and we don't need the energetic resolution at all, let's say. Yeah. So depending on the task, we will select the certain type of the detector. And let's start with, sorry, with the liquid scintillation counting or spectrometry. It is very powerful technique because it has very high efficiency. So it is one of the parameters, yeah? that is important. It has very high efficiency to detect alpha and beta emitters. So in principle, what is the liquid scintillation? We have some organic solvent, aromatic solvent, and in this solvent there is an organic scintillator molecule. So the scintillator converts the energy of ionizing radiation to the visible light that we detect with the photomultiplier tube. So, and when again the concentration of the scintillator is only 1 to 2%, so the main component of this system is solvent molecules. That's why the ionizing radiation firstly interact with the solvent molecule. The solvent molecule become excited, and they transfer this energy of excitation to the scintillator molecule. So it's transfer of energy. And the scintillator molecule emits visible light that we detect. Unfortunately, there can be negative side effects in the system that we call quenching, and it can be chemical quench and color quench. I will show you later the result of this quenching. And it's the typical vials that we use for liquid scintillation counting. They can be either glass vials or usually we use plastic vials. They are more convenient to use. And there are just some examples of the of spectra that we obtain with the liquid scintillation spectrometry. You can see that this beta spectra, they have this even distribution from the 0, let's say, to the maximum energy of the beta particles. Alpha particles, they have very good shaped the discrete spectra of the alpha particles. But sometimes on this spectra, you can see the presence of these sharp peaks, but they are not result of the alpha particles interaction with our cocktail, scintillating cocktail, but it is the conversion electrons. The conversion electrons, it is electrons that are emitted due to the conversion of the energy of, let's say, that normally emits as gamma quanta, but this energy transferred to the electron on the atomic electronic shells, and these electrons are knocked out from the atom. And as far as the energy of this gamma transition is as a fixed number, the electron energy in the atom is a fixed number. The energy of the knocked out electrons is also some certain fixed number. That's why these conversion electrons, they have a discrete spectra, discrete lines on the spectrum, and very often people really can think that it is alpha particles, but it's not. Don't forget about the conversion electrons. Don't mix them with the alpha particles. So what are the quenching effects, chemical or color quench? It is the situation when if in your system some chemicals that can catch this excitation energy are present, then this energy transfer from the solvent molecules to the scintillator molecules can be disturbed with these additional chemicals. They can catch this energy, and your scintillator molecules will not be excited, will not emit light. So you will lose some part of the light that should be emitted, but will not be emitted due to the catching of the energy, capturing of the energy by these chemical impurities. Normally, it's some some chlorine-containing organic molecules or nitrate-containing groups, organic molecules, so something like that. Another type of quenching, color quench, that means that even if your scintillator molecule is excited and there is emission of the visible light, you can have some colored impurities, like iron-free, for example, or other colored impurities that can absorb your emitted light, and again you lose your quantum of your photon, and it will not reach the photomultiplier, so you will not detect this light. What does it mean for the system, for the detection system? If you lose some number of photons, the number of photons that emitted in very short period of time for the detection system means the energy of the initial particles that excite the whole system. The higher the energy, the more photons will be emitted. Yeah, the more molecules will be excited, the more photons will be emitted. And if you lose some photons for the system, it will mean that the energy was lower, the initial energy of the particles. That's why the peaks in your spectrum will be shifted to the left. Yeah, so you will be confused with the shape of the spectrum first. But also, if the quenching is strong enough, you will lose so many photons that you will count less events than you have actually in your system. So you will not only have the change in the shape of the spectrum, but also you will have the lower number of the pulses of the event. So you will lose the efficiency, the counting efficiency in your system. But to deal with these quenching effects, normally we have different parameters, quenching parameters, that we can use to calibrate the efficiency of our system. So normally with the liquid scintillation spectrometer, you will receive the number of the standards, sometimes with the quench standards. You can build this quenching curve. And when you measure your sample or your real sample, the system will tell you what is the quenching parameter in your system. So it is the technique. I will not describe it here, but if you want, I will explain you. The equipment will show you this quenching parameter, and with this quenching parameter, you will automatically calculate the efficiency of your system, the counting efficiency of your system. So, but before you need to make this calibration before the measurement, okay? At least, I don't know, once in a week or a month, depending on how often you measure your sample. Okay. But liquid scintillation has another advantage. It can distinguish between the alpha particles and the beta particles. So for the due to the different production of the number of molecules that are excited and the time for the system that is required to go to the initial state, depending on was it alpha or beta particles, you can see that in the case of alpha particles, this time for the system to go to the initial state is longer than for beta particles. So that means that if you have a signal from your system, you can measure it with the so-called time discriminator, for example, pulse discriminator. And you can say that, okay, everything that was measured before this time, it was a combination of both alpha and beta particles, but everything that is measured after this period of time in the signal, it is pure alpha particles, yeah? Only from alpha particles. And by subtraction of the amount of the alpha particles in your spectrum from the combination of alpha and beta, you will obtain the pure beta spectrum. And here it is example of this discrimination. So it was measurement of the one sample containing both alpha and beta emitters. So it is strontium 90 with the yttrium 90, and I don't remember what was as alpha emitter, but you can see that it is not one spectrum; it is two separate spectra that were detected for the same sample at the same time, but with the use of this discriminator. Yeah. Okay. Again, this Cherenkov radiation can be used for counting of some radionuclides that have the maximum energy of beta particles more than 300 kiloelectron volts, and of course with different efficiency. But the advantage of this method that you don't need any liquid organic scintillator. You just need the water. You put your sample in water. If you have, for example, on the with the chemical separation, you have on the strontium 90, and you can put it directly in water and measure it. You can wait some time, 2 weeks, for reaching equilibrium with the yttrium 90, yeah, because it is progeny of the strontium 90. And when the equilibrium will be reached, the efficiency of the counting of yttrium much higher So you can count lower activity of strontium after 2 weeks due to the presence of yttrium-90, yeah, after equilibration time. So, and you will need only water again, so nothing expensive in your system. These liquid scintillation cocktails, they're quite expensive now, but with Cherenkov counting, you don't need them. But of course, you cannot use Cherenkov counting for everything. You cannot use it for alpha emitters. You cannot use it for radionuclides with the low energy of beta particles like tritium, carbon 40, nickel 63, or other radionuclides. But in some cases, it is quite convenient. And in the most of the spectrometers today, there is a very easy, very simple, but very efficient coincidence scheme. That means that we use two photomultiplier tubes to measure our sample. Why it is important? Because the photomultiplier tubes they have their own noise signals and quite high number of pulses of this noise in especially in semiconductor photomultiplier detectors. But if we have two photomultiplier tubes, we can combine them in so-called coincidence scheme. That means that the signal that comes together from two photomultiplier tubes at the same time. So there is some very small range period of time, something like a few microseconds. Only if the signal will come in this period of time from both photomultiplier tubes, only this signal will be detected. If it goes only from one tube and there is no signal from another tube, then the signal will not be detected. Yeah, because it will mean that it is a noise signal from one photomultiplier tube. But signal from two photomultiplier tubes will mean that it is signal due to some events in our sample. So there is a flash of light and signal goes immediately from two PMT. Thus, we can reduce significantly the background in our measurement. And it is important for measuring some low active samples. And it's just an example of the most common spectrometers that are used everywhere. I think either it is American production, Perkin-Elmer, or it is Hydex from Finland. Of course, there can be some local producers. In Russia, we have one producer of such techniques, but very simple with only one vial to measure at once. But still, you can have it in your country maybe. But the most popular spectrometers are produced by these two companies. And nowadays, Perkin-Elmer also has this trademark of the Quantulus spectrometer, if you heard about it, the low background counting spectrometer. Now it is also Perkin-Elmer, but before it was a product from Finland. But nowadays it is a USA product. Alpha spectrometry. As you remember, alpha particles have very low penetration range, even in the air. So that means that if there is a layer of air between the sample and the detector, then a lot of alpha particles will be absorbed by this layer of air. That means that we should remove air between our sample and the detector. And to do this, we use a vacuum chamber. So we vacuumized our chamber, so there is very little pressure of air, so no alpha particles will be lost during the detection. And to measure alpha particles, not only by liquid scintillation spectrometry, but with the high resolution of the energy of the alpha particles, we used mainly silicon semiconductors that have not brilliant energy resolution, but sufficient resolution for detection of the alpha particles. It's something like 30 kilo electron volts. So it's too much, for example, for gamma spectrometry, but very enough for alpha spectrometry, because as you remember, alpha particles have energies from 4 to 8 mega electron volts. So 30 kilo electron volts, it's very nice resolution for our system. Also, you can suppress some negative effects. For example, if you usually we don't use high activity. Why? Because we remember about the recoil nuclei. So if we have a high activity, the recoil nuclei that are formed in our samples can go to our detector. And this recoil nuclei, many of them, they are also radioactive. And if they go to the material of our detector, they will be there for the rest of our life. So this detector will be contaminated with the radioactive recoil nuclei if we use high activity. But we can suppress these negative effects by controlling the pressure of air in our vacuum chamber. If we increase air pressure inside the chamber, yeah, we have now not so good, maybe energetic resolution, but due to the air pressure, this recoil nuclei, they will not reach the detector. So modern equipment can control this air pressure, and you can use different air pressures depending on the sample that you measure. And one of the important thing when we measure alpha emitters with these vacuum chambers, it is the preparation of the good thin sample, because otherwise, if we have a thick sample, alpha particles that goes from this sample will lose energy to go from this sample, and we will obtain not a good peak, sharp peak, but we will obtain the peak with this very long tail. And it is okay if we have only one radionuclide, but if we have a combination of different alpha emitters and we want to measure all of them, just imagine that there will be another peak with also long tail, so it will be very difficult to analyze this bad spectrum. So very important to prepare very good thin sample, either by the electrodeposition, so it is electrolysis of your sample, or by microprecipitation. So this is electrodepositions, just one of the scheme. You have the aqueous solution of your separated alpha emitters. You have the stainless steel disc, or you can use other metal disc. It can be nickel, for example, or I don't know what you have, what easier to you to have as a metal disc on the bottom of this vessel. And you have a platinum wire here. So it is anode, it is a cathode, and you just switch on the electric current here and wait sometime maybe 1 hour, 2 hours, depending on your methodics. And on this cathode, as far as it is cathode, so it's negatively charged, you have a very thin layer and a very homogeneous layer of the cations that are absorbed on these disks, and then you just switch off your electric current and take this disk out, dry it a bit, and measure. Or you can use micro precipitation technique. So there are filters, just cellulose filters, if I remember correctly. And these filters, there is a layer, very thin layer of the either cerium or lanthanum fluoride or barium sulfate. And actinides, they very efficiently co-precipitate on this very thin layer. And thus, by just passing your solution through this filter, you have a precipitation on this layer of your actinides, very thin layer of your actinides. And you will get a very good resolution in your spectrum. So it's very convenient technique, but again, it requires to buy these filters. So it's not very cheap. So this is a cheap one. This is expensive one. It takes a lot of time. It takes much less time. So it depends on your possibilities. What you do you have a lot of money or not? Yeah, you can choose what is more appropriate for you. And this is just an example comparison of the energetic spectrum of the radium sample obtained with the alpha spectrometry with the good prepared sample. You can see very sharp peaks of different radionuclides, and the spectrum obtained with the liquid scintillation spectrometry. So you can see that the liquid scintillation is not really spectrometry. That's why, because the resolution is not very good, that's why we usually call it liquid scintillation counting. So we just count the activity of our sample. Okay, so these are just, again, an examples of different chambers for alpha spectrometry. And now let's go to the just very brief discussion of the gamma spectrometry. Again, when our gamma quantum interacts with matter, if you remember, if we have a photoelectric effect, yeah, we have the total absorption of the energy of gamma quanta and the release of the photoelectron. And this photoelectron and the secondary ionization processes can be detected by our ionization detector. So we detect the current, electric current, and we can say that this electric current is proportional to this energy of gamma quanta. So by calibrating our electric current in the detector, we can determine the energy of the initial gamma quanta. Okay, so here it's a photoelectric effect. It is good effect because we absorb all energy of gamma quanta, so we can easily say what was the radionuclide that emits this gamma quanta. But actually, in the gamma detector, it is not only photoelectric effect, but the, for example, Compton scattering. Yeah. But the Compton scattering and the absorption of the scattered photon, this second scattered gamma quanta, it also can be catched inside the detector. Yeah. And these processes, this Compton scattering and the absorption of gamma quanta, they are very fast processes. So for the detector, all this scattering and absorption looks like one event, because the time resolution of the detector is not sufficient to see different processes. They are too fast for the detector. Okay, so all these events scattering, absorption for the detector looks like only one event. And as a result of these events, the total energy of gamma quanta is absorbed. Yeah, again, the total energy. So again, all these energies are equal to this initial energy. So due to the either photoelectric effect or by the cascade of these different effects, we measure so-called photopeak. That means that the total energy of the gamma quanta of our initial gamma quanta. But of course, due to the Compton scattering, this scattered gamma quant can be released from the detector and not be absorbed by the detector. So we lose this part of energy. Yeah. And it is not some certain number, not a certain value of energy. It is some stochastic distribution of the energies. And that's why on the gamma spectrum, we always see this Compton scattered gamma quantas or Compton pedestal or Compton continuum in our spectrum. If we talk about the efficiency of the detectors, again, depending on what type of radionuclides we would like to measure, we can use different types of the detectors. Either coaxial, it is most popular detectors again, or planar detectors. Planar detectors, they're good to detect the low energy gamma quanta, or even we can say already X-rays. But it is a very specific task. It is important if you are working with the natural radionuclides, for example, with lead, with some other radionuclides. But for many applications, when we are measuring content of the radioactive waste, normally it is enough for us to have a very simple coaxial detector. It has quite good efficiency for almost all radionuclides that we have in radioactive waste. Yeah. So again, depending on what the task of your research, you can choose different detectors. Of course, it is good if you have in laboratory both types, but again, they're very expensive today. It's not easy to buy everything that you want. Semiconductor detectors like high purity germanium detectors, they have perfect resolution for gamma spectrometry. It's something like 1.5 kilo electron volts for high energy area of the gamma spectrum. And if you compare it with the scintillator detectors, you can see that the scintillator detectors like sodium iodide, for example, they have worse resolution than any semiconductor detectors. But the scintillator detectors, they are much, much cheaper. You can buy scintillator detectors for, I don't know, 300 US dollars, and it will work perfectly. But if you need to analyze radionuclides with the very close energies, then you cannot use these scintillator detectors, or you must make this chemical separation. So again, depends on the purpose. What do you need to do? For example, if you measure only, I don't know, very popular cesium-137 in the system, and it is the only radionuclide that you have in the system, and you measure it, you don't need high purity germanium detectors. The scintillator detector will be enough. But if you would like to measure all the natural radionuclides, including thorium decay chain or uranium decay chain, then you will need very good energy resolution. So everything depends on the task. You remember this Bremsstrahlung radiation from the beta particles, yes? And the Bremsstrahlung intensity is high when the energy of the beta particles is high and the atomic number of the target is high. And you can see, so there is an example of liquid scintillation spectrum for this strontium yttrium sample. And we can see the similar energy in the spectrum of the gamma quanta, but it is not a gamma quanta, yes? Strontium and yttrium, they don't have any gamma radiation. They're pure beta emitters. But even with the gamma detector, we can see this radiation, that is Bremsstrahlung. So if you have in your sample of radioactive waste a big amount of not only strontium and yttrium, but any type of the beta emitters with the high enough energy of beta particles, like strontium, like phosphorus. But phosphorus is short-lived, but anyway, phosphorus 32, for example, then even in your gamma spectra, you will get this Bremsstrahlung type of radiation. And maybe it's not problematic for you, but if you want to measure, for example, cesium-137 in the same mixture, it will be something like this small peak in this Bremsstrahlung continuum, and it will be much difficult for you to find it and to measure it. So to remove the Bremsstrahlung, you can use special filters. For example, you can put just some additional aluminum shielding on your detector, and aluminum will not produce such a lot of stopping radiation or this Bremsstrahlung radiation because it is a light element and it stops efficiently electrons from this decay of strontium and yttrium, but it doesn't produce the very intensive Bremsstrahlung. So you can decrease this noise that goes from your sample. So now about the destructive characterization, because for both for alpha spectrometry or for liquid scintillation spectrometry, you will need to obtain your pure radionuclide, pure alpha emitters, or let's say pure beta emitters. And for beta emitters, it is good to have the individual elements of these emitters. So how to do it? With the destructive methods. So all the radiochemical analysis methods, they include some homogenization of your sample with adding some tracers. Tracers are important to calculate the chemical yield of all your operations before the measurement. Then there is sample pretreatment, depends on if you have a liquid sample or a solid sample. For liquid sample, you can pre-concentrate if it's necessary by evaporation or precipitation or whatever. Or if you have a solid sample, then you must dissolve the solid sample or leach your radionuclides. And only after this, you can use some separation methodics. It is precipitation, ion exchange, extraction, and extraction chromatography. And only after this, you prepare your counting source. Either it is vial with this liquid scintillation cocktail, or this very good thin sample for alpha spectrometry, whatever. And then you measure and you calculate the chemical yield with tracers, and then recalculate the activity of your sample. So tracers, they if it is possible, it's not always possible, but it is good if it is possible to use the isotope of the same element, but with maybe shorter half-life, or at least the isotope that is definitely not present in your sample, like plutonium-232 or plutonium-236. It's a good tracer for plutonium. Or you can take neptunium-239. It is produced easily from the radionuclide generator from americium-233, for example, if you have it in the lab. So these tracers, they normally don't present in your radioactive waste samples, but they can be easily measured afterwards in your spectrum, from your spectrum, and you can recalculate the chemical yield of all the operations since the very beginning, and it is necessary. Don't forget to use tracers when you make this destructive radioactive waste characterization. So why we need the destructive characterization? Usually, again, it is when we measure pure alpha and beta emitters. Otherwise, we cannot measure them without it. Or if we measure some metals, stable metals in our samples also, then we use this destructive analysis. And it can be used actually for any kind of samples, what you have in mind. And how we make this destruction. First of all, the very simple, the cheapest way, but again, the longest way, it is just the acid digestion. Then you just take your sample and boiled it with acid for several hours or days, depending on your sample. And to do this, depending on the sample that you are analyzing, you can use different acids or combination of acids. Normally, we use nitric acid. If we need to dissolve organic, we can add some perchloric acid, for example, or if we need to dissolve some silicates, for example, in soil or in other materials, we can add some hydrofluoric acid. So depending on the sample, you can use different combinations of these acids. So again, it's a quite cheap method for destruction, but takes some time. To facilitate, to make it faster, you can use microwave digestion. So it's, in principle, it is the same method, but with use of autoclaves in microwave, that makes it faster. But advantage of this method, it's not only that it's cheap, but also you can put a big amount of the sample in your glass. Yeah, you can use 1 liter glass, put there, I don't know, 10, 20 grams, 30 grams of the soil, and boil it for several hours or days. And you have nice solution with enough activity in your glass. But with microwave digestion, usually you have few grams, maybe 5 grams of your soil, not more. Yeah, so it is fast method, but there is some limitations. But if you have a radioactive waste, 2 grams will be enough for you. Another methods that is also very fast and have very high efficiency to make the solids, to transform them into liquid, it's fusion. So it is more expensive than microwave, but it is very, very efficient. Again, for different kind of samples. You can use different fluxes. So you just mix your sample with some flux, the desired flux, and you heat it up in this equipment. There is a melt of your sample and your flux. That is further is put it in the aqueous solution, and you have a pure aqueous solution of your sample. Again, you can use not a big amount of samples, but you can completely destroy them in a short period of time. So after the destruction of your sample, of your solid sample, then you can choose one of the separation methods for your radionuclide. All the separation methods, they have so they're heterogeneous systems, so they have a boundary between two phases. Yeah, they have this border between two phases, and this is border between either liquid and solid. It is precipitation, ion exchange, chromatography, or it is two immiscible liquids, so in extraction, or it is gas and solid, for example, for gas adsorption or for sublimation of some radionuclides. Then it is necessary again if you try to analyze difficult to measure nuclides, so that means that it is pure alpha and beta emitters, so no gamma lines from them, or if you have a lot of let's say contamination, like in the example of the Bremsstrahlung of strontium and yttrium. If you have a very high amount of strontium, you would like to separate it to be able to measure other radionuclides. So, or for some application, you use it, of course, for purification of radionuclides. So let's go with the precipitation. Let's start with precipitation. So normally, precipitation means that we have insoluble or hardly soluble compound, and we can calculate the solubility of this compound using the solubility product of our material. And if in our conditions, in our solution, the product of this concentration is more than this constant of solubility product, then we observe the precipitation. If not, then there is no precipitation. And these solubility products, they are constant. You can easily find them in databases, and you can easily calculate, will you see the precipitation or not? And if not, then you can use carriers for your radionuclide. Very often for short-lived radionuclide or for radionuclide at very low concentrations, we cannot precipitate them directly, because we will not reach this solubility product, because their concentration, for example, will be 10 to minus 15, and let's say for silver, even for silver iodide, it will be a high concentration of the iodine that we need to have in our system. So it will be not possible to precipitate it. But to make it possible, we can add some carrier that will help co-precipitate our radionuclide. And there are three main types of carriers. So it's isotopic carrier. So it is the same element, but stable isotope, or at least a longer lived isotope. For example, if we would like to precipitate uranium, I don't know, 232, we can add just uranium 238. That is, let's say, not stable, of course, but we can consider it as a stable isotope in this case, and we can use it for co-precipitation. So why it is easy and very efficient? Because it is the same element. Yeah? So all the isotopes of the same element, they have very close chemical properties, and they will be precipitated together. So it is the most efficient way to precipitate, but it's not always possible. For example, if we would like to precipitate radium, there is no stable isotope of radium, and thus we can choose and we can use element with the very similar chemical properties. In this case, it is barium, yeah, like Marie Curie did it more than 100 years ago, co-precipitation of radium with barium sulfate, and it is called non-isotopic, yeah, carrier, because it is another element, but specific non-isotopic carrier, because it is this carrier has the same or very similar chemical properties as our radionuclide. And there is a third case, so-called non-specific, non-isotopic carrier. Very often we use iron oxide, as Natalia Kuzenkova presented for you, or it can be manganese oxide or rare earth fluorides, for example. These precipitates, they have, of course, different chemical properties with the actinides, but they are efficiently catching all the multivalent cations, including actinides. So it is very efficient. So it is absolutely different chemical properties. It is non-isotopic carrier, but it efficiently catches actinides and other polyvalent cations. So we can use this precipitation technique either to concentrate our nuclides from the big volume of the liquid, for example, or we can remove other radionuclides that make it very complex to make the spectrometry of our radionuclides. And there is a list of carriers already that you can use to separate your desired radionuclide. Again, this co-precipitation is used as a part of the further measurement technique, like in these filters. Again, these fluorides and sulfates, they are very efficient to precipitate actinides and other polyvalent cations. So precipitation is very simple and convenient. You can use it to concentrate from the very high, from very big volumes of the liquid samples, and you can make it very selective. But precipitation means that you have to precipitate your sample, then you filtrate it. So it's really a time-consuming technique. And sometimes you use too much carriers, so you need to optimize your methodics not to increase the volume of radioactive waste. And yeah, so due to this time consuming and a lot of operations like precipitation, pH adjustment, filtration, removing precipitate from filter, then dissolving the precipitate, it's not really very technological. So it always balance of benefits and disadvantage of your methods. So solvent extraction or liquid-liquid extraction, you can call it in both ways. It's a very popular method. You can find it everywhere, from lab in analytic or organic synthesis to the technology for production of metals, bioproducts, or whatever. So in principle, in solvent extraction, you mix two immiscible liquids, you shake it, you try to mix it. Of course, they are not mixed completely. There is a very small emulsion produced during the shaking. But sooner or later, when you stop shaking, these two liquids, they form two separate layers. And it is not always that the organic solvent is less dense than aqueous solution. Sometimes you can use more dense organic solution like chloroform or other halogenated diluents, and they're denser than water, so they will be in the bottom of your system. So just a few terms that we will understand each other after the shaking of the our aqueous feed solution with the organic solution that contains extractant and diluents. Usually, sometimes it's just pure extractant, but okay. So after this mixing and then settling down, you have organic phase that we call an extract, and you have the rest of the aqueous phase that we called raffinate. And if you want to take your radionuclide back from the organic solution to the aqueous solution, you make the back extraction or stripping, depends if you have further steps. If you completely back extract your samples, then it is back extraction. If there is a mixture of different components and you extract only one of them, then you strip your organic solution to obtain your some individual components. And anyway, it called this aqueous phase called back extract. So solvent extraction can be very selective because if you remember this lecture on Tuesday, yes, on Tuesday, there were examples of different organic molecules that are specific for certain metals. So it can be very selective. And this method is very technological. You just put two currents of one of the organic solution and one of the aqueous solution, and you mix it, and they are separated automatically, let's say, just naturally, because of they are immiscible and they have different densities. So it's very simple technological procedure. And as far as you can find very selective extractant, you can reach very high partition coefficients that will be independent on the radionuclide concentration. And again, after the separation of your radionuclides, you can easily back extract your radionuclide into aqueous phases. But again, it is always a balance of advantages and disadvantages. The disadvantages that usually we use flammable solvents or toxic solvents. There is a production of the organic waste that are not very easy to handle because organic waste is difficult to be incorporated in, for example, cementitious matrices. So this is one of the drawbacks of these methods. If you have many elements that you must separate, then you will have multiple extraction steps in your process. Then next method is chromatography. Chromatography is again very basic method in analytics, and oops, okay. So in principle, you have, I will go further. You have a contact of the aqueous phase with the, let's say, organic stationary phase, but you repeat it many times. When the aqueous solution go through the column, it is not only one contact, but it is continuous repetition of this contact of the aqueous phase. So it is sorption, desorption of your components when it goes through the column. So it is so-called dynamic mode, and that means that you repeat multiple times the same process. And as far as you repeat the same process many times, you reach very high separation of the two components. To do this, we can use either organic sorbents that we call resins, or it can be some inorganic sorbents. But let's go to this organic resins. Normally, we have two groups, two types of the resins. Either it is cationic exchangers or anionic exchangers. Yeah, in the case of the cationic exchangers, it is some acidic groups, either sulfur groups or carboxylate groups that exchange cation, the H plus, the proton, exchange with the cation of the metal. Yeah, so that's why it's cation exchange resin. In anion exchange resin, there is either quaternary amine groups or some N-heterocyclic groups that, like pyridine groups, that form these cations, nitrogen-containing cations, with some counter anion, like chloride, that can be exchanged with the anion, like pertechnetate, for example, if we analyze it in our system. And to quantitatively describe the process of the separation, we use, as usual, distribution ratio of the radionuclide. So it is a ratio between the concentration of the radionuclide on the surface to the concentration of the radionuclide in the solution, with the combination of the volume to mass ratio of volume of our solution and mass of our sorbent. So it is some constant for our certain conditions. And if we would like to see how efficiently two components separate with each other, we can use this ratio of two distribution coefficients. Ion exchange is a very simple and efficient method. You just need a column and you put your solution through the column, you collect your sample, that's it. So it's a very high chemical recovery because this dynamic mode, multiple repetition of the process, and it's really can be easily scaled up from the lab to industrial condition. But for this separation, as far as we use, I will go shortly here, as we use only limited number of groups, either it's sulfur group or carboxylate groups, there is no high selectivity towards different components. So to separate two components, we either have to control very narrow pH conditions, or we need to again repetition of this separation. And thus, again, as far as resins, they are organic materials, we generate this problematic secondary radioactive waste. And the combination of the extraction and ion exchange, it is extraction chromatography. So in this method, we combine the efficiency of the dynamic process of the ion exchange or chromatography. So it's a very efficient dynamic process, but in conventional ion exchange, the selectivity is rather low. But we can use the extractants, like in liquid-liquid extraction, that are very selective to our specific radionuclides. And by combination of these two advantages, we can use extraction chromatography that is at the same time is a dynamic process, so very efficient, and uses the selective extractants, so very high selectivity. And the properties of extractant that we used are the same as in liquid-liquid extraction, because it is absolutely the same molecules. So normally we have some inert support, porous support, where you place your extractant, your molecule, selective molecule with the diluent, and then you evaporate the diluent, and there is a pure extractant molecule in the pores, and you make a columns like these, small cartridges with your resin, yeah, covered with the extractant molecule, and you pass the aqueous solution through this small cartridge and separate your radionuclides. There is an example of commercially available resins that are used for certain radionuclides. So if you know which radionuclides you would like to separate, you can just can use this table and use the appropriate resin. Just briefly, the explanation of how different resins work. This is actinide resin, so it contains this complex phosphonic acid, and it has very high affinity, so very high distribution coefficients for all actinides in the diluted acidic conditions. So we can use this resin, for example, to make a pre-concentration of actinides from the large volumes of liquid acids. Another example is TEVA resin. So TEVA means tetravalent actinide resin. So it's from the name, it means that it is very efficient for separation of tetravalent actinides. So tetravalent thorium, neptunium, plutonium, uranium. But you can see that as far as it is, it contains this amine group in very low acidic conditions. It works as an anionic exchanger, so it can absorb not tetravalent actinide, but the technetium in the form of pertechnetate. So by changing the just acidic conditions, you can separate technetium and tetravalent actinides with the one resin. Another example is UTEVA, so it's uranium and tetravalent actinide resin. So it has a very high selectivity to hexavalent uranium and tetravalent other actinides. But it is interesting that if you switch conditions from nitric acid to hydrochloric acid, you will get the very big difference between the thorium tetravalent and uranium hexavalent sorption. So we can use this resin not only for pre-concentration, let's say, of this element, but also by changing conditions by separation of the uranium hexavalent from thorium tetravalent. And one of the last example, it's strontium resin. So from the name, it is obvious that it is for separation of strontium 90 or stable strontium, whatever. You can see that this cavity of this specific crown affair is very selective to strontium over other either monovalent cations or divalent cations. Maybe there is some problematic with barium, but at a high concentration of nitric acid, or like 10 mol per liter, you can see that even in this case, the separation of strontium and barium is very high. So you can use it efficiently for separation of strontium. So again, there are advantages of methods. It's very selective. You use very small columns to separate your radionuclides, so it's very productive. But of course, as in the case of ion exchangers or liquid extraction, you produce organic radioactive waste, but in smaller volumes. These resins quite expensive again, and these resins they are bleeding because it is not a covalent bonds between extractant and the support inert support, but it's just absorption, yeah, of extractant in the pores of the of this support. And that means that with the aqueous flow, you step by step take out this extractant from the pores. So these resins are bleeding, so we cannot use it many times. Maybe 2-3 times is okay, but you cannot use it 10 times or more. So, and they're expensive again. So there's a short summary. First of all, we remember that if we would like to measure so-called difficult to measure radionuclides, that means again pure alpha and beta emitters, we must make these separation steps. Otherwise, it will be not possible to determine them. There are several methods like precipitation, ionic exchange, solvent extraction, extraction chromatography can be used. Don't forget to use tracers to calculate the chemical yield of all your procedures. And yeah, you can use precipitation and solvent extraction as a separation step, so for pre-concentration, and then you can use this extraction chromatography or ion exchange for very precise separation of the radionuclide. Okay, that is all for this lecture. Thank you for your attention. Again, if you have any questions, I will try to answer them. Thank you. Yeah, please use mic.
First of all, thank you for the interesting information. Could you please repeat again why we don't use high activity when we use alpha spectrometer?
Yeah, so if you remember, when we have, when we have alpha emitters, there is a recoil nucleus that also produced due to the alpha decay. And this recoil nucleus has energy of 1 to 200 kilo electron volts. So it means it's quite a high velocity of this nucleus. When you have a sample, you have, of course, flux of alpha particles that goes to your detector, but the ionizing radiation, it goes not only in the direction of your detector, yeah, it goes everywhere. That means that your recoil nuclei, they will go not only in the opposite direction to the detector, but they also will go to the direction towards the detector. And that means that this recoil nuclei will go to the detector, and the big nuclei, they will be penetrated in the material of the detector. So they will be there forever. And this recoil nucleus, when we are talking about the alpha emitters, that means that they have daughter radionuclide that are also radioactive. So this recoil nuclei, they are also radioactive. That means that you incorporate radioactive material inside your detector. And that means that you will have very high background in your measurement. Even if you will not, when you will remove your sample, the radioactive recoil nuclei will produce a lot of noises in your detector. So your detector will be destroyed very soon.
One thing I would like to know is why is useful the back extraction? Why to have this back extraction back to the
Because at the end we have to prepare the sample for measurement, And it is much more easier to work with the aqueous solution than with organic.
Okay.
That's the main reason.
Okay. Another thing is about the quenching. You show us a diagram where, let's say, for plutonium, I think it was better, and for carbon was a little bit worse, and for tritium much worse.
Yes.
But is this quenching effect is I think it's proportional to the this one is proportional to the activity that we have.
No.
No.
Okay. It almost independent on the activity. It depends on the property of your chemical composition of your solution. It doesn't really dependent on the concentration of radionuclide, and it depends on the energy of the particles that you measure. So tritium has the lowest energy of the beta particles. That's why the quenching is the most important for tritium. It is the maximum 18.6 kiloelectron volts for tritium. For carbon 14, it is already 156 kiloelectron volts, so it's, let's say, 10 times higher energy, maximum energy. But still, the quenching is very important for some samples. So the maximum efficiency for carbon is something like 90%, maybe 85%. For tritium, it is not more than 60%. But if you have beta emitters with the energy more than 200 kiloelectron volts, let's say, then the quenching will be not so important. The efficiency will be more than 90%, and it is okay. You can see that for alpha particles, the quenching has almost no effect because of the properties of the alpha particle to excite a lot of molecules around. The quenching will be not so important. So the quenching is very important for beta emitters with the energy less than 200 kiloelectron volts. Yeah, like nickel 63, also some other materials. In many other cases, you can forget about it. Only if you don't have, let's say, black solution, the light will be absorbed inside the sample.
So the experiment, in order to have all these points for one isotope, it's not to give a different activity each time.
No. You use one sample, and you put some chemicals that will quench your spectrum. You made it by yourself.
You put more and more concentration.
Yeah. You measure pure solution, then you add a bit of this chemical, then put more, and you obtain this dependence. Yeah, because this parameter, the important part of this abbreviation is this letter E. It is external standard. That means that you measure the spectrum inside your vial, but this spectrum produced by the external gamma source. So you measure the properties. Why it is possible? Because I remind you, one of the mechanisms of interaction of gamma radiation with matter, it is Compton scattering, where a lot of Compton electrons are produced, and these Compton electrons, they are like beta particles inside your cocktail. They produce a lot of light inside your molecule, so inside your cocktail. So you have external gamma radiation that irradiates by gamma quanta your sample, and it produces a lot of Compton electrons inside your vial. And as far as you know, the gamma source, this standard, external standard, you know exactly what should be the spectrum of these Compton electrons. And you compare this spectrum, ideal spectrum, with the spectrum that you observe in your real sample. And and the machine recalculate it to this parameter that we call TCE. And you use this parameter to calibrate this parameter with the efficiency. And then when you measure your real sample, again, it is always this external irradiation before the measurement. Machine determine this parameter TCE, determine the efficiency, and then external standard goes out, and there is a measurement of your sample with the known efficiency. That's it.
And another more thing, you show us that we can use also glass vials, but also plastic vials. The plastic vials aren't more intransparent to the
Yes.
light.
Yes, but there is another important characteristic of plastic. Yeah, here we don't have this, but if you will look on the diode lamps, yeah, in other rooms maybe. Diode lamps, they have very small spots. LED, LED, very small. But you can see if you have this plastic shield, it looks like homogeneous. So the very good characteristic of plastic vial that this plastic material make the illumination homogeneous. So it reaches this photomultiplier tubes let's say homogeneously, independent on where is your nuclide is located. But it is not the case for glass vial. So the glass is more transparent, yes, but you really need to make a precise geometry inside the glass vials to have the same conditions for measurement. It is not the case for plastic vials because they make it this homogeneous illumination. So it's for me, it's more convenient to use plastic. Yeah.
Thank you very much.
If there is no more questions.
Okay.
Okay, thank you.